Hi everyone. Our group will discuss the New York City Fair prediction. Our group includes Colin, Rachel, Sean, Tyler, and myself, Joyce. First, let's start with the problem description. The main goal of our project is to have the ability to predict a New York City cab fare at a given time and a date of any year. In our prediction, we're considering few variables such as distance traveled and the numbers of passengers. Our data set contains two other predictors listed as the following. The first predictor being the day of the year with a standard year range starting at January 1st being number 1 until December 31st being number 365. The second predictor is the day of the week starting on a Sunday as number 0 and ending on Saturday as a number 6. The third predictor is the time of day including hours 24, minutes 60, and seconds 60. The fourth predictor is the distance traveled in which we apply change in the longitude and change in the latitude. Finally, the number of passengers. Table 1 shows the breakdown of variable type and what the actual variables are. For our quantitative variable in the interval scale, we have day of the year, time of the day by hours, minutes, and seconds. For the quantitative variable ratio scale, we have distance traveled and number of passengers. For our qualitative data, we have day of the week. And as you can see in figure 1, that's a histogram showing the fare price in which we are mostly under $25, except with the exception of few outliers. If we look at these figures, each figure describes a comparison. Figure number 2 compares the day of the year versus the fare amount in which there is no defined correlation. Figure 3 compares the day of the week versus the fare amount. There's very small difference. If you can look closely, you'll see the box plots are extremely shrunk due to the extreme high fare amounts. Figure 4 compares the hours of the day versus the fare amount. Please keep in mind that our data is based on universal time, which is 4 hours ahead of Eastern Standard Time. Figure 5 compares the distance traveled versus the fare amount in which we are able to see a coloration or a linear shape to an extent. Figure 6 compares the number of passengers versus the fare amount in which the fare drops as the number of passengers increase. If you look closely, you will also see box plots are still extremely shrunk due to the high fare amounts. And now I'm going to pass it on to Colin.
To evaluate our models through cross-validation, we use the validation set approach by splitting our data into two sets, one with about 80% of the data and one with 20% as our train and test data sets. And those are both saved as two separate CSV files for analysis in R. To measure performance, we are looking at the residual sum of squares, R squared, and mean squared error to determine how well our models fit the actual data. To begin, we wanted to build a regression model that would help tell us what our fare amount would be given all of our predictors. So initially we started with each predictor on its own and walked through a forward selection to determine the best fit of predictors. To begin, we noticed that distance traveled really cut the RSS in half compared to all the other predictors. So this seemed to be the most significant and was the first one that we chose. We saved this as its own model so that we'd be able to model just distance traveled to fare amount. Next, we stepped through all of the other predictors and got the best RSS, starting with distance traveled and ending with hour of the day. However, in this case, we do have a lot of predictors, so this model might be a little bit too flexible. To compare to this, we tried a simplified version with really the most significant predictors from the previous model, those being distance traveled, day of the year, passenger count, day of the week, and minute of the day. In this case, the RSS only had a very small change, so this kind of gives us 3 sets of data to start with in terms of prediction. To add a few more, we wanted to look at some interaction terms. So since we had broken time into 3 separate variables, we figured let's start by using some interaction between those 3. So we were able to compare minutes of the day times hours of the day times seconds of the day to create one model with interaction. And we created another model using some nonlinear terms. We noticed that the passenger count plot versus fare amount seemed to be parabolic. So we decided to use a passenger count squared as our nonlinear term. So this would be our 5th model. So all 5 of these models will be run through our cross-validation validation set approach a few slides further. And to go along with our regression, we wanted to do a second model, which is a natural cubic spline. We chose this because we noticed that in the plot you see to the right here of distance traveled versus fair amount, there's a clear shift in the trend between about under 1.25 and after 1.25. So we decided to put a knot right at 1.25 to hopefully model this data using two separate functions. To evaluate all of these models, we compared them with the factors we mentioned before, the RSS, the R squared, the mean square error for the train and test sets. So for all of the regression models, using only distance traveled, all of the predictors through forward selection, our simplified model, our interaction model, and our nonlinear model, they all had very similar RSSs, R squareds, and mean squared errors. You can see, interestingly, that when we moved from the train set to the test set to predict the test set, we had about a 5% increase in the mean squared error, which is not too bad. For our natural spline model, however, we had a nice change here. We had a nice R squared of almost 0.7, which indicates a fairly good fit to the data. And we saw that the mean square error was very close between the train and test set, meaning that this model seems to fit the data very well and give us a nice prediction of our fair amount.
I'm going to go over a little bit of a discussion here. Since we are working with the regression problem, our objective is prediction. Here we have a sample data point going from the Empire State Building to the Rockefeller Center at around noon UTC on New Year's Day 2021 with 5 people. The following are the variables included in this data point, which include ESB 40.74, negative 73.98, RC is 40.75, negative 73.97. Distance traveled is 0.0173. Day of the year is 1. Day of the week is Friday, which is 5. Hour of the day is 12. Minute of the day is 2. Second of the day is 15. And the passenger count here is 5. Continuing on with discussion regarding the models. After running the first model, just using distance as the only variable, we can see distance is statistically significant because the probability is extremely low. In other words, distance affects taxi fare price. After completing forward selection, we can see which variables are statistically significant and affect cab fare. Variables circled are not statistically significant when using 0.05 as a cutoff probability. Probability must be less than or equal to 0.05 to be significant, meaning we cannot say if these variables affect the fare.
In this slide, we are going to be discussing the simplified model and the interaction model. Again, the circled variables are not statistically significant in the two models, meaning we cannot say whether or not these variables affect fare prices. All other variables with probabilities less than or equal to 0.05 affect cab fare given the model. So now we're going to be looking at the nonlinear regression and the spline regression. Again, the circled variables are not statistically significant in the first model, meaning we cannot say whether or not these variables affect fare prices. All other variables affect cab fare given the model. And then in the spline, as you can see, both are significant and they do affect the cab fare.
We have all of our models.
So now we're going to be looking at the nonlinear regression and the spline regression. Again, the circled variables are not statistically significant in the first model, meaning we cannot say whether or not these variables affect fare prices. All other variables affect cab fare given the model. And then in the spline, as you can see, both are significant and they do affect the cab fare. So now we're going to be looking at the nonlinear regression and the spline regression. Again, the circled variables are not statistically significant in the first model, meaning we cannot say whether or not these variables affect fare prices. All other variables affect cab fare given the model. And then in the spline, as you can see, both are significant and they do affect the cab fare. So now we're going to be looking at the nonlinear regression and the spline regression. Again, the circled variables are not statistically significant in the first model, meaning we cannot say whether or not these variables affect fare prices. All other variables affect cab fare given the model. And then in the
In addition to
spline,
this, there
as
was
you can
many
see, both
outliers
are
within the
significant
data.
and they do affect the
So,
cap
for
fare.
example, there might have been extremely high
So
fare amounts.
now we're going to be
for
looking at the
example, higher than
nonlinear regression and
$100,
the spline regression.
or
Again, the circled
unusually
variables are
long
not
distances
statistically
that traveled
significant in
outside
the
of New York
first
City that
model,
wouldn't make sense
meaning
for
we
our
cannot say
predictions.
whether or not these variables